Welcome back, Algebra 1 students. This is your first lesson of Topic 4, Systems of Equations and Inequalities. I think this is a pretty cool unit. It's not quite the end of semester 1, but it's pretty close. And I think it's a cool unit because it's the culmination of everything you've done so far. Topic 1, you learned how to solve equations and inequalities. Topic 2, you learned how to graph. Topic 3, we discussed some functions and added on to our knowledge of graphing and writing equations. And now topic 4, we put it all together. So, what we're going to do for the first 5 lessons or so, and I think there are 7 total lessons here, the first 5 lessons are all about how to solve systems of equations. And you're going to learn 3, maybe even 4 different ways to solve. And then we're going to move into systems of inequalities. So very similar to the first unit where first we learned equations, then inequalities, we're going to do the same thing here. So let's start with the opener, and then we're going to go back and discuss what a system of equations actually is. Tiana and Brittany decide to start saving money for college. Tiana begins with $10 and adds $5 per week to her total. Brittany, on the other hand, started with more money. She had a generous aunt who gave her $50. Brittany decides to only save $2 a week since she started with a decent amount. Write an equation to represent the total amount of money Tiana has saved, T of n, after an unknown n number of weeks. Then do the same for Brittany, creating an equation using b of n and n. And there's a hint, slope-intercept form. So notice we're using that function notation that we covered the last couple classes, and we called T of n probably for Tiana's money after n weeks, and we're using B of n for Brittany's money after n weeks. So as we go through T of n, let's see what happens here. It looks like Tiana begins with $10, and then she adds on $5 per week. Now in the past, you might have written that as 5x. And although there's nothing wrong with that, I think for now I'm going to call this 5n, because this n here is our input variable. It tells us the variable that should be in our equation. Now, I did also mention slope-intercept form, and this will become important later. Don't forget we can switch this order, and we could say that this is 5n plus 10. They're the same thing there. All right, let's see if we can do an equation for Brittany's money. All right, Brittany's money, generous aunt who gave her $50, so she starts with 50, and then she's only adding on $2 per week. All right. Part B. How much money will Tiana have after 6 weeks? And what about Brittany? Well, the way we show how much money Tiana has after 6 weeks is we say Tiana's money of 6, Tiana's money after 6 weeks. And as a reminder, this function notation just means take the 6 and replace the input variable n with that 6. And I'm just going to work to the right. This becomes 10 plus 30, that's 5 times 6, which is $40. After 6 weeks, Tiana has $40. What about Brittany? Well, b of 6 is going to be 50 plus 2 times 6. Yeah, that becomes 50 plus 12. That looks like $62. So it's not too much of a surprise. Brittany started with more money, so she has more money after 6 weeks. But then an interesting question in part C. Will Tiana ever have the same amount of money saved as Brittany? Why? And if so, after how many weeks will that happen? Well, I think you could probably convince yourself that Tiana will have the same amount of money saved as Brittany, right? Because Tiana, although she's starting way back with $10 as opposed to 50, right? Tiana, though, is gaining $5 per week. Eventually, I'm not sure how long, but eventually that $5 per week is going to erase the deficit between 10 and 50, that extra $40. The question just becomes, after how many weeks does it happen? So you should probably try to pause this video right now and think, will she ever have the same amount of money as Brittany? Okay. Well, what you could probably try here, even though this might take a while, is couldn't you go through and just try different numbers for n, right? You could say, well, maybe I could try after 10 weeks, and you do 10 plus 5 times 10. That's 10 plus 50, and that's $60, right? And then you do the same thing with Brittany, and I'm just using the colors here so we can see it. 50 plus 2 times 10, that's 50 plus 20, that's $70. Nope, not the same yet. It looks like Tiana still has less. You're like, okay, I'm bumping it up to 20, right? 10 plus 5 times 20, that's going to be 10 plus $100, which is $110. Then you try Brittany's, and you have 50 plus 2 times 20, and that's 50 plus $40, and that's 90. Oh, well, at some point between 10 weeks and 20 weeks, Tiana has surpassed Brittany. But the question was, after how many weeks exactly will that happen? Now, you could keep guessing and checking, but what we did here, where we were comparing two different equations and trying to figure out where those two equations are the same, is ultimately what we are doing with a system of equations. So let's get down to the lesson. Looking at multiple equations at once is known as a system of equations. The solution to a single equation makes the left side equal to the right. The solution to a system of equations, however, must work in every equation. So when I say work in every equation, it means you need to look at every equation and your solution has to make the left side equal the right. So for example, we have a system of equations down here. Systems of equations are very commonly written using these curly braces to group these equations together to show them that we should look at them as a single problem. Now, if I wanted to see if these over here, these coordinates are solutions, we need to remember back how we figure out if something is a solution or not. Well, to determine a solution, don't we just substitute in our numbers? Also remembering that coordinates go x comma y, I think we can see what we need to substitute in. So my first equation up here is y equals 2 times x plus 1. And when I substitute, the y is 1. I don't need parentheses around that because nothing else is happening to it. And then on the other side, 2 times something plus 1. The x here is 0. I will tell you that many students switch the order around for the x and the y because they say, oh, x then y, and they switch them. So just be careful there. I will also tell you that a calculator or some mental math will make this go quite a bit quicker because you can just work one side at once. Here's the left side, nothing's changing there. And then the right side, if you can do this all in your head or on the calculator, it might go a little faster. If not, you can try to show each step, but there's not a lot of work here. Room to work here. 2 times 0 is 0, 0 plus 1 is 1. Oh look, 0 comma 1 made the left side equal to the right. So, if those two are equal, then does that mean that this 0 comma 1 is a solution to this system of equations? Well, no, actually, because a solution to a system of equations doesn't just make the first equation have the left side equal to the right, it also needs to work for the second equation, y equals negative parentheses x plus 2 minus 3. And so I'll do the same thing here. Y is 1, and then on the right side, I'm going to fill in everything, just trying to color coordinate here. The x is 0. And again, I'm going to do everything mental math style, or you can do it in a calculator too, because I'm just running out of space here. 0 plus 2 is 2. Make that negative 2. Negative 2 minus 3 is negative 5. Is the left side equal to the right? I don't think so. So we put that slash through and shows that it didn't work. So this point here, 0 comma 1, is not a solution to this system of equations. Now at this point, you should pause this again and try the other three that are here. You get the idea. You can quickly try them and see which ones work. Now, a few reminders. If this one had not worked, if the left side had not equaled the right like so, you wouldn't have to try this second one because we're looking for a point that works in both equations, and as soon as it doesn't work in one, don't try the other. That's an extra step you don't need to do. Second, just because you find one that works may not mean that that's the only one that works, so you need to keep checking the others. Ready, set, your turn to try, go. All right, so I'm going to quickly run through these over here. I'm not going to take too long. I'm actually just going to straight substitute everything in right away and then go from there. So let's see. So we had something equals 2 times something plus 1. And then over here we had something equals parentheses plus 2 minus 3. And I'm going to do that each time. So it equals 2, right? I'm just setting all these up just because I'm trying to color coordinate and be as efficient as possible. There we go. And here's my last one. And then the nice part is we can just substitute in whatever these numbers are and be okay. All right, so the first one was, I'll do this in red again, 0, 0. And we had to simplify and see what happens. The left side's easy. The right side, 0 times 2 is 0, plus 1 is 1. Those are not equal. Ha! This 0, 0 didn't work in my first equation. I'm not even trying it in the second one. Let's try part C. Part C, negative 5 in for x, 0 in for y. Don't need to simplify. This is negative 10, right, plus 1, which is negative 9, not equal again. Cool. And then last but not least, we had, let's see, negative 2 and negative 3, so that's not changing. And then on the right side, this is negative 4 plus 1, which is negative 3. Ooh, cool. This one worked so far. Let's try the second one. Second one, we have negative 2 for x, negative 3 for y. Nothing's changing on the left side. The right side, some mental math. Negative 2 plus 2 is 0. Negative 0 is still 0. 0 minus 3, negative 3. Ooh, this one worked too. Oh, that's so exciting. This point, negative 2, negative 3, is a solution, maybe there are more, is a solution to the system of equations. Now, hopefully you're starting to see a little bit of an issue here, because I gave you 4 coordinates. And how did I choose those 4 coordinates? Well, it could have been random. It's not in this case. But I think the odds, if you just picked 4 random coordinate pairs and one of them being the answer, that's pretty slim. There's an infinite number of coordinate pairs, right? What about 100, 1 million? So if I hadn't given you the solution to the system of equations above, how could you have found the answer? Well, and one thing that might be jumping out to you is that these are coordinate pairs. And coordinate pairs often show up on a coordinate plane, on a graph, on a grid. And in fact, if you look closely at these equations, you might be able to tell that this first equation is in mx plus b, and the second equation is in hk form. And those might suggest graphing. And if you were thinking graphing at all, kudos to you, because it turns out that you can solve a system of equations by determining the correct coordinates by first graphing each equation. And actually, let's do that first before we fill in the last blank. So just a quick reminder, we're going to graph something that's in the form of y equals m times x plus b. There are only 2 steps. My first step is you begin at b equals 1, right? That's our y-intercept. It is the point 0, 1, right here. And then step 2 is you use the slope, right? That's our movement, and our slope here is this guy up top, 2 over 1. Up 2 to the right 1. There we go. And we can continue that pattern, up 2 to the right 1, or left 1, down 2, and so on, so forth. And there is my first line. Don't forget that a line has to be continuous, so we connect those points over here. And there we go. Let's go ahead and graph our second equation. This second equation is in HK form. Okay, HK form, just a friendly reminder, that's our mx minus h plus k. I can see my h and my k. I think for the m, we should probably put that invisible 1 here. Okay, and let's do the same steps. So step 1, I'll do this one all in blue. Step 1 is we begin. This one doesn't give us the y-intercept. It gives us a full point with x, y that's generally not the y-intercept. The opposite of h, that's negative 2, comma k, negative 3. Negative 2, negative 3 is this point right here. And then the second step is we again use the slope. And our slope in this case is the value that's out front, negative 1. Let's turn it into a fraction. And we need to go down 1 to the right 1. Down 1, right 1. And it looks something like this. Perfect. Well, if you had to guess, what do you think we look for if we graph two separate lines and we're trying to find the coordinate pair that makes both of them work? Well, a coordinate pair makes an equation work if the left side is equal to the right. It means that this point is on this line and on this line. It's going to be on both of the lines. Looking at the graphs over here, how would you describe the place that contains the point that is on both of those lines? Hopefully you would say, oh, we are looking for where those lines intersect, or for their intersection. The intersection is this spot right here. Well, then based on the graph, the solution to this system of equations is, and let's write this out, the x is -2, the y is -3, because that is where the two lines intersect. And so hopefully that puts today's title into perspective. Today's title is Solving Systems of Equations by Graphing. And so if you wanted to find exactly where Tiana and Brittany had the same amount, what could you do? You could graph one equation and the other and figure out where those two equations intersect. Honestly, at this point, you really have a pretty good foundation of what we're doing for the next couple days. We have learned one method to solve a system of equations, and that's by graphing. You're going to get some good practice on that in just a second. However, there is one more piece that you need to be comfortable with, and that is the fact, or the types of solutions that can occur with a system of equations. This semester, our system is only going to have two equations, and they are going to be linear. Don't forget that linear just means they form a line when you graph them. Well, then there are three options for your solutions. Like our example on the previous page, your system of equations could have one solution because the lines intersected at one point. However, we have two other options. You could have a system with no solution, or you could have a system with infinitely, sorry, you have to write small here, infinitely many solutions. In fact, I bet you guys are clever enough to figure out what those graphs will look like. So on part A, go ahead and sketch a graph of a system of linear equations with no solution. And then go ahead and write your two equations down below. Well, you might be thinking, what does it look like for a system to have no solution? Well, this has one solution because they intersected in one spot. So no solution must mean the lines never intersect. What has to happen for two lines to never intersect? Oh, they have to be parallel. So let's go ahead and write one line pretty easily. Okay, what y-intercept do you want to use? I'll use a y-intercept of -1, and then I'll just use a slope of up 1 over 2. Okay, and you could have used anything here. I'm just kind of winging it like this. There we go. If I wanted to write that equation, we could, let's call this equation f of x instead of y. You could use y. There's nothing wrong with that. This is f of x equals, let's see, let's think slope-intercept form here. So my slope was up 1 over 2, and then there's the x. And then my b right here is -1. So you could have said y equals 1/2 x minus 1 f of x. Great. But that's only one line. A system of linear equations needs a second line. So let's pick a different y-intercept. How about 2? What do I have to do from this point to make sure it never intersects the red one? They have to be parallel. Parallel lines have the same slope. So I'm going to go up and down at the same rate as the first. And there we go. This second line, just to tell the difference, I'll call g of x. Let's write the equation. Okay, g of x, let's see, has that same slope, but then a y-intercept of +2. Easy enough. All right, last but not least, Sketch a graph of a system with infinitely many solutions. Well, infinitely many solutions. No solutions they never crossed. One solution they crossed once. Infinitely many. Doesn't that mean they cross an infinite number of times? So for them to cross an infinite number of times, what does that mean? Well, I mean, I guess one way is we could have kind of a squiggly line here, and then, I don't know, maybe a straight line here, and this squiggly line like crosses an infinite time. But we aren't doing any squiggly curves. They have to be linear. So let's start with one function and see if we can go from there. So just to do something different for this function, I'm going to start over here, and I'm going to use a negative slope. Let's go down 1 to the right 3, up 1 to the left 3, up 1 to the left 3. Now if you connect these, if you use the slope of down 1 over 3, you might notice that it doesn't cross the y-axis at a nice point. You're like, ooh, is that 1? Well, no, it's actually not 1. I'm just a poor artist at times. So if I wanted to write this first equation here, and we can just go back to y if you would like, this would be y equals, I think if you don't have a nice y-intercept, HK form is probably the way to go. We already saw the slope, down 1 over 3, and then we just need a point. Doesn't matter what point. We could use this guy over here. This is the point 4, 0. So x opposite of h plus 0. Some of you might say, do we need the plus 0? No, you don't. You could actually write it just like this if you wanted, and that's totally okay. I'm just putting the plus 0 so we can see and remember HK form. Now, how do we get a line that intersects or crosses us an infinite number of times? Well, what if I just did a line exactly on top of it? Here is a point on the purple graph, and here is the same point on the green graph. Therefore, they are crossing an infinite number of times. Let's write an equation. Now, you could write exactly the same equation, or we could be a little bit more creative. The slope has to be the same, but let's just pick a different point. What if I picked this point, -2, +2? Opposite of h plus k. These two are actually the exact same equation. It's pretty hard to see, but they are exactly the same, right? We built them the same way. They make the same line. Now you might say, well, that's silly. Why would you have two lines that cross each other? But there's lots of occasions where two different things could be happening and they'd actually create the same thing, right? Maybe as my job as a teacher, I get a particular pay raise every year, and someone else, let's say a nurse, hopefully they make more than I, but a nurse gets the same pay raises. So if we graphed our two salaries, they might be exactly the same even though we have different careers. All right, so at this point in time, the rest of this lesson is really all just extra practice for you. So it's nothing too terrible. I am going to record myself going over this, but I'd rather you try it on your own and then just quickly fast forward to see if you got the answers correct or not. So good luck for the rest of this. Unpause me if necessary. Ready, set, go. All right, in-class practice, which of the coordinates are solutions to the following system? We did this on the previous page. Not too bad. I'm just going to zoom in quickly, and I'm going to do the same thing as before, where I'm going to set up each of these. So on this one, I have 3 times something minus 2 times something equals 4. And on this side, I have something equals -2 times something plus 5. Right? And I'll just go through and do that each time because we're going to have to try this each time. Now, a couple tricks of the trade. If this is a system of equations and one of these doesn't work, either none of them will work because there will be no solution, or only one of them will work. So as soon as I find the one that works, I can actually stop. Because we saw for systems of equations, you can either have one answer, no answer, or infinitely many answers. Those are your only 3 options. There can't be anything else. So we will try to narrow this down in just a second. And we're seeing how I can multitask. I probably messed everything up, but that's all right. So we'll start with the 0, 2. And I'm going to do this one on this left side. So 0, -2. X is 0, and notice that x came first here, and y is -2. Again, mental math or using a calculator is going to save you. The 4 stays. This left side, this is 0. -2 times -2 is +4. 4 equals 4. We're good so far. Okay, I'm on a roll here, so I might as well just do the rest of these. 0, 5. Okay, well, 3 times 0 is 0. Negative 2 times 5 is negative 10. Negative 10 is not equal to 4. That's actually good. We don't need to try the other side, and we're done there. Let's keep it up. We have our point 2, comma 1. X is 2, y is 1. A little bit more math here, but not bad. This is 6 minus 2, and 6 minus 2 is 4. So that's looking good. Last but not least, 1, comma 3. X is 1, y is 3. Okay, this is 3 minus 6. 3 minus 6 is negative 3, I think. That's also not equal to 4, and so we're done with that one. We're down to 2. Okay, well, we have the point 0, comma negative 2 here. And this one went y equals, so this is our y, this is our x. Negative 2 stays. On the right side, 0 plus 5 is 5. Negative 2 is not equal to 5, so that's not an answer. And hopefully this is it. Now be careful, because if this isn't it, it does not mean there's no solution here. It could just mean we haven't picked the right 4 coordinates yet. But hopefully I'm not that mean. Y and x, let's see how I did. This is negative 4 plus 5. And negative 4 plus 5 is positive 1. This one also works. There we go. There is my solution. Now, you could have gone through and graphed this, of course. You could have graphed each equation. They would have intersected at 2, comma 1. But it is important to remember how to check solutions, too, because sometimes if someone says, oh, you're looking at these 2 equations, I think this is the answer. Instead of going through the whole process to find the answer, sometimes it's easier just to plug the answer in and say, nope, you're wrong, or, oh, yeah, you're right. All right, let's move through. We have some actual graphs now. Here we go. Graph the following systems to find the solution. All right, let's do each of these. So y equals negative 4x plus 5. This looks like slope-intercept. I'm starting at 1, 2, 3, 4, 5. And my slope is down 4 over 1. 1, 2, 3, 4. We go to the right one because we want our line to be going down. This is a negative slope. Negatively sloped lines go in a downward direction. And I'm going to continue this out. Trick when you're graphing, try to do as many points as possible, because that way you can see the exact spot where these are going to graph. And I'm kind of off the screen here, but that's fine. Same thing the other way, up 1, 2, 3, 4 over 1. All right, there's my green one. I'll connect them later. Here's y equals 3x minus 9, hopefully in blue, negative 9. And then we have positive 3 over 1. So up 1, 2, 3 over 1, up 1, 2, 3. That's where they intersect. We got it. I'm going to continue through just so I can try to make a nice looking line, but we already know our answer here. It is nice still, I think, to connect your lines just to remind you that they are a continuous function, and to remind you that apparently I'm not very good at connecting lines. That's a little better. Got squiggly at the end, but that was fine. And then same thing the other direction. Okay. We can see that they intersect at this point right here, and that point has an x of 2 and a y of negative 3. If you really wanted to check that, you would plug 2 in for the x, negative 3 in for the y, and make sure the left side equals the right. All right, let's try our next one. It looks like we have 2 equations. We can do HK form here for my first one. HK form has the hidden point positive 2, comma 1, 2, comma 1 like so. And then we use our slope to go down 3 over 1, down 1, 2, 3. And then ask yourself, if you go left 1, would your line be going down? No, it's a negative slope, so we want to go down 1, 2, 3 to the right 1. 1, 2, 3 to the right 1, 1, 2, 3 to the right 1, and we'll go the other way, up 1, 2, 3 to the left 1. There we go. And then we'll do our last one in, we'll go in yellow, I guess, 2x minus 3, slope-intercept form. Negative 3, up 1, 2 over 1, and we continue it out. We can already see our answer here. They cross at that point. Again, I really like to continue the line. I think it looks better, a little bit more professional. It is up to you, though. We can definitely see that they intersect in one spot, and it looks to me like this spot is the point positive 2, comma 1. All right, just a couple to go. I think we're doing all right. 2 equations left here. You'll notice I left you some extra space, though, because these 2 equations are a little bit trickier to graph. And there's a few different ways to do it. I'll show you both ways. I'm going to do this first one, and I'm going to take up pretty much all the space over here. I'm going to do this first one in blue. So we're going to do x plus 3y equals 6. And I'm actually going to convert this one to slope-intercept form, just again to remind you how to do that. To convert to slope-intercept form, we need to make sure that this is y equals everything else. Right now there are two numbers attached to y. 3 is multiplying, x is adding. So let's undo that adding x first. And don't forget that there's a 1 here. So I'm going to subtract 1x from each side. These cancel, leaves us with 3y equals, and then 6 minus 1x is fine, but since we're going for mx plus b form here, I'm going to put the x's first. So negative 1x and then a positive 6. Finishing this off, to finish isolating y, we need to divide both sides by 3. Now don't forget, anytime you multiply or divide, you need to distribute, at least this semester. So I'm going to distribute the division to each side, or to each term. Negative 1 doesn't divide nicely by 3, so we keep it as negative 1/3. 6 does divide nicely by 3, and that's positive 2. So my top equation up here in slope-intercept form is y equals negative 1/3 x plus 2. Right? Don't forget, you don't know the slope here. It looks all nice and dandy till you move it around. We don't know the slope until y is alone. So we start at positive 2 and go down 1 to the right 1, 2, 3. And I'll continue that out. 2, 3, and that's about as far as I can go. Up 1 to the left, 1, 2, 3. Up 1 to the left, 1, 2, 3. Up 1 to the left, 1, 2, 3, and there we go. There is, of course, a separate way to do this, so I'm going to tackle this bottom one over here, x minus 3y equals 6. And the separate way to do it is to find the intercepts. Oops, that's not very even. To find intercepts, okay, we can find the x-intercept and the y-intercept. The x-intercept is always found by finding an x, and the y-intercept, not so surprisingly, wants you to find the y. So to find your x-intercept, notice the 0 is in the y position. So in my equation, I need to replace y with 0. This is x minus 0 equals 6. I think that's just x equals 6. So that tells me that my x-intercept is 6, comma 0. 1, 2, 3, 4, 5, 6. Actually, that's really nice because that's where the two lines intersect already. But let's finish off the y-intercept just for the good practice. The y-intercept has the 0 in the x position. Right, I'm just starting with this equation each time. 0 minus anything, there we go. And then divide off that negative 3. Don't forget the negative, most common mistake. Y equals negative 2. So our y-intercept is 0, negative 2. There are my 2 points. You can connect them, or you can even see the slope. Up 2 over 1, 2, 3, 4, 5, 6. So down 2 over 1, 2, 3, 4, 5, 6. Now at least we have an extra point to get a good idea of this line. There's my first, and here is my second. Oops, much too steep. There we go. Looking pretty good. Ha. And we should be able to tell that they intersect at the point 6, comma 0. All right, last one. Y equals 4 and y equals negative 2x. You don't actually need a bunch of space here, but I'll show you a couple tricks. So let's get to it. Y equals negative 2x. And let's separate this like so. First one we'll do in purple. Y equals negative 2x. Looks very similar to mx plus b. It's just missing the b. So let's give it a plus 0. There's nothing adding. We can always add 0. And then graph. Start at 0, down 2, to the right 1. We'll finish this off, moving a little bit faster. There we go, or up the other way. Perfect. 1 down, 1 to go. Y equals 4. Now, there are, again, a couple ways to take care of this. Maybe the fastest way is if you remember y equals 4 is a horizontal line. But I know not everybody remembers that, so I'm going to add in what's missing here. What's missing to make this in the form y equals mx plus b? Well, you might say, well, there's an x and a b missing. But what if I wrote it like this? Y equals something and then plus 4 at the end. How many x's are in this problem? Well, there are 0 x's in this problem. And so you could treat this as 0 to make it into a fraction over 1x plus 4. Start at a y-intercept of 4, go up 0, and to the right 1. And so we can see that this horizontal line is indeed going to cross the purple graph once I can figure out how to draw a somewhat straight line. Decent. And so it looks to me like they intersect or cross at the point -2, 4. Now, so far, we've represented our systems of equations as either two equations or two graphs. But just like when we wrote equations, we sometimes see our two equations in different forms. For example, what if you were given two equations like so, where here's the graph of one and the table of the other? Well, if we wanted to find where these two intersect, we can see one line, but it's harder to see this line. Couldn't we see this line, though, just by graphing it? So let's go ahead and graph each of these points. My first point is this one, 3, -1. So we go right 1, 2, 3, and down to -1. Then we have 1, 1, -1, 3. And in fact, can we even see the slope here? It looks like it goes down 2 over 1, down 2 over 1. But let's do the last one, -3, 1, 2, 3, 4, 5. In fact, I think it even goes down 1 over 1. Can we fill in those extra blanks here? And so, when we graph our second equation, does it cross the first equation? Well, certainly. I believe they intersect at the point 0, 2. And there's our solution. Yeah, so if you're given a graph and a table, it should be pretty easy just to plot the table onto the graph, and then you should be able to visually see where they intersect. Let's try a couple more. I'm going to go ahead and plot these. We'll keep that same color scheme going. 2, -1, 2, 3, 4, 5, 6. Very nice. 1, -1, 2, 3, 4. And in fact, I think that's probably enough to get the slope, right? The slope looks like this, but let's check the rest. -1, 0, and -2, 2. Yeah, the slope continues. Down 2 over 1, down 2 over 1, down 2 over 1. There we go. And if we connect, we can definitely see that they intersect at the point 0, -2. All right, moving on. Oh, good. A couple more of these. These aren't bad at all. And as a hint, you will definitely have one of these on your test and maybe even on your daily quiz. So hopefully you slam dunk this style question. All right, 5, 1. 1, 2, 3, 4, 5, 1. Nice. -1, -1. We can do that. -1, 2, 3, 4, -2. And -7, -3. 1, 2, 3, 4, 5, 6, 7, -1, 2, 3. Well, I think we get the idea. It's a little bit off the screen, but it shouldn't be too bad. What's the slope? Up 1 over 3, up 1 over 3, up 1, 2, 3. Yeah, there we go. Always nice to be able to see the slope. That way you can connect and be pretty accurate. It looks like they intersect at the point 2, 0. All right, let's do one more. 7, -4. What is with these 7s? 1, 2, 3, 4, 5, 6, 7. Down 1, 2, 3, 4. There we go. 4, -2. 1, 2, 3, 4. -2. 1, 0. And -5, 4. 1, 2, 3, 4, 5. Up 1, 2, 3, 4. This one could be a little bit trickier, but I'm guessing it intersects at this point. Let's see if that works with the slope. If I go down 2 to the right 3, down 2 to the right 3, yeah, I think that follows the slope all the way through. So sometimes you can kind of cheat with it and say, well, it looks like it crosses here and test that slope. That is the point -2, 2. All right, the last part of today is just 4 different systems of equations, and you have to do 2 things. The first is pretty darn easy, and we're going to tackle that all together really fast. We have to state the solution of each one of these. The solution is just where they intersect. So, for example, graph 1 intersects at 2, 2. Graph 2 is at -1, 1. Nice practice writing our points, right? -2, -2, and -1, -1. Nice. But then the trickier part that we need to continue to practice is how to write the equations. Well, and I'll match the color coding here. I'll do the green and green, the red and red. If you have a nice y-intercept, we can use slope-intercept form. I'm going to call this green one f of x just to be clear. You can call it y, that's fine. So let's go ahead and tackle all of the green ones first because I think they all have nice y-intercepts. So for my green one, we get f of x equals, starts at 0 and goes up 1 over 1. So I think my slope is 1 over 1 x, and then up 1 over 1. The y-intercept is 0, so plus 0. In fact, a lot of times you would see this equation, I'll use y really quickly, without the 1 over 1 because you don't have to write the 1, and without the plus 0 because you don't need to write that either. A lot of times you would just see this equation called y equals x because we know that there's a 1 and a 0. Very, very common equation. All right, let's do the rest of the green ones. So this one, this next guy, f of x equals, well, it has that plus 0, which we know we don't need to write. In fact, it looks very, very similar to this one, except it's sloped the opposite direction. So I think instead of a positive 1 over 1, this is a negative 1 over 1, or just a negative x. For graph 3, also goes through 0, up 1 over 1. Oh, cool. So this is just the function y equals x. And the last one is exactly the same as well. Nice, that saves some time. All right, let's do our second equation. You can call it g of x or y or whatever sounds good to you. Notice that g of x does not have a nice y-intercept for any of them. So we need to go through and use a nice point on the graph. Where could we find this nice point? Oh, look, don't they intersect at a nice point on all of them? In fact, aren't these all nice points on there? So I think the only thing we really need to find then is the slope, and we can fill this in. But I'm actually going to leave the slope blank to start and just do my HK form setup really quickly because I'm going to use HK since the y-intercept is not a nice number. Right? We don't want to guess at the y-intercept. And you can use slope-intercept form if you can find the exact y-intercept. But since we already have a nice point, let's just do this. HK, opposite of h plus k. Opposite of h plus k, opposite of h. Now when I say plus k, this is really, and I'm going to erase this, so be careful, plus negative, but a positive and a negative right next to each other just make a negative. So plus k, if it's a minus 2, we put minus 2. If it's a minus 1, we put minus 1, and it looks like this. Those look pretty darn nice. We just need to fill in our slopes. We'll do that one at a time. Okay, here's my first point right here. I have no idea where my next nice point is. I think it was supposed to be down 1 to the right 1, 2, 3, probably here. Up 1 to the right 1, 2, 3. So let's just call that 1/3. It doesn't seem perfect on my screen, but I think that's all right. Graph 2 looks like it's up 1 over 1, 2, 3 as well. Very nice. Graph 3 is also up 1 over 1, 2, 3. Cool. Nothing bad at all. And graph 4 is going in a downwards direction, so I know the slope is negative, and it looks like it's down 1 to the right 1, 2, 3. And we're set. So nothing too terrible for today. As a quick recap, we learned that a system of equations is when we look at multiple equations at the same time. We are ultimately looking for the solution to this, and the solution occurs in one of three ways. Number one, it is the single coordinate pair that makes the left side equal the right. Or there will be no solution, there will be no coordinate that will work in both, or every coordinate pair will work in both. Visually, what's happening is if we graph the two equations, we can see that they cross in one spot, one solution, in no spots, no solutions, or in every spot, infinitely many solutions. So thank you for tuning in on a heavy day for graphing. The next couple days, we're going to learn ways to do this using algebra instead of graphing, and we'll even have a really cool day to bring this all together. Good luck with your assignment for tonight, and I'm excited to have you back next class.